My name is Yushe. I'm from University of Leeds, UK. So I will give a talk on DNS of flame instability and the cellular structure of lean hydrogen combustion. So firstly, I'm very grateful for Dr. Jin Fang and Dr. Xiaojun Gu from Scientific Computing Department, the Raspberry Laboratory UK, for their help on the DNS modeling code. So firstly, about the background. So as we know, the lean hydrogen flames may exhibit intrinsic instabilities such as thermal diffusive and the Darcy-Nando instability. So this instability can make the original smooth flame to become cellular structure. So therefore the cellular structure can will develop along the flame front and characterized by the ongoing growth and diffusion and contributing to the increased flame surface area and increasing propagation speed. And even in some cases, this instability can introduce supersonic behavior through deflagration to dilation transition. And then the research objectives, we want to understand this phenomena using DNS modeling with detailed hydrogen kinetics, focusing on the morphological characteristics and turning the self-acceleration of hydrogen flames. So we are going to use the two-dimensional DNS software to study the data that cannot be measured in experiment, such as the more precise gas velocity and gas various species and combustion products. And we also want to study the relationship between the species and the morphological structures of the flame front. So about the methodology. So firstly, as I said just now, we will use a two-dimensional compressed Navier-Stokes equation with line transport equations for species, and this is solved within the framework of the finite difference method. And then we are going to use open source software, the advanced flow simulator for turbulence research called Astro. And then the chemical source terms are calculated using the chemistry ODE solver. And the line species mechanism is also used for the hydrogen combustion kinetics. So the boundary is symmetry and the long reflective. The condition is 1 bar and 300 Kelvin degree. So this is just the initial try. So we maybe do more tests in the future. So only 2 cases over there. So the physical space is just 60 times 60 or 60 times 60 millimeter, and for equivalential 0.4, we contract 1024 times 1024 grades for this case, and 2048 times 2048 grades for the equivalential 0.6. Because when we increase the equivalential from 0.4 to 0.6, the flame thickness will decrease. So we want a finer mesh for the richer mixture, even they are both lean condition. So this is the evolution of the temperature profile of hydrogen air flame at the equivalential 0.4, the upper picture. So the lower picture is equivalential 0.6. So as you can see, for both cases, the flame front is originally is smooth and stable, and the flame front transition towards to instability and cellular gradually. And as we can also see, the cask-like structure persists and involves, and the cells with cells undergoing enlargement and the division. So this kind of structure is self-similar fractal. So in combustion, we call it a fractal theory. And so we want to do some compression between them. So when we change the equivalential 0.4 to equivalential 0.6, we can see the flame front is not that cylinder and not that irregular. It's because the Lewis number. The Lewis number is the ratio of the thermal diffusivity to the mass diffusivity. For equivalential 0.4, the effective Lewis number may be just about 0.42, and for the equivalential 0.6, the effective Lewis number is about 0.63 maybe. So when we change the equivalential, essentially it means we change the effective Lewis number. It means we change the competition between the thermal diffusivity and the mass diffusivity. So, and then we further generate entire round flame structure using the mirror method in take plot from a quarter flame, just I showed just now in DNS. So you can see the entire round flame from over there. And and I also compare the DNS results with the PIV mean scattering pictures. For the equivalential 0.4, we can see that the flame structure using DNS is more wrinkled compared to the mean scattering. But for 0.6, the extent of wrinkling of structure using mean scattering structure or mean scattering is more wrinkled than in 2D DNS. So the conclusion, we can conclude that the mean scattering picture is more irregular and asymmetric than the DNS modeling. We further calculated the flame speed at the isotherm of temperature just 5 degrees above the environment. So we can see that in the figure A, the flame speed decreased firstly due to the high Mach number, and after instability, the flame accelerates in housing pattern. And then we also quantified, and we also plot the gas velocity map on figure B. We can see that the higher gas velocity at the convex part, just marked as yellow color. We can see that, and the lower gas velocity at the concave parts, marked as blue or green, yellow. And then we also put forward a parameter, the gas flow disturbance intensity. And then we plot the flame wrinkle surface area against this gas flow disturbance intensity at the flame radius at 65 millimeter in the lower figure. So we can find a similar trend between each other. The both DNS and the PIV show that the increased wrinkled flame surface correlates with the higher gas flow disturbance intensity. Even we can see some discrepancies here. Maybe we haven't done enough simulations here. Maybe we can do the conditions. For example, from lean to rich condition, we can see whether they are consistent with each other or not. We also do some analysis on the species and the heat release rate. We want to find whether there is a correlation between the species and the structure due to the instability. Firstly, it's the heat release concentration. I'm not sure whether you can see it clear or not, but we can see at the convex part, it's marked as yellow. So it means the highest heat release rate is concentrated at the tips of the convex and the cusp like structures in hydrogen flame. And this area represents the most intensive combustion activity. And the figure A to figure and the figure B and the two lower figures is H and OH and all species. So we can still see the similar a similar map as heat release rate. They are predominantly found in the convex regions, and which means they are high reaction rates. So we also conclude we also can conclude that the high mobility of H species disrupts the diffusion balance, leading to the flame instability with increased structure, and also the OH and O generation. We also plot the H2O and H2O2 and HO2. They are uniformly distributed within the burn gas region, so nothing new here. And then we do the curvature analysis here. We want to see we want to use curvature to quantify the morphological characteristics of the flame front. So as we can see in figure C, it's the evolution of the originally smooth flame to the highly wrinkled flame surface. So the figure C is a relationship between the percentage of the flame front and the wave number. So the positive wave number means convex. The negative wave number means concave. So at the very beginning, you can see the wave number distribution just centered around 1. It means the flame surface is smooth. And when the flame propagates, we can see the wave number range expanded. It indicates the increasing wrinkle. So and then we compare the curvature data between equivalential 0.4 and 0.6. And we also do the PDF analysis based on the curvature. Firstly, we compare the results between different equivalential ratios. So for equivalential 0.4, we can see a wider upper and lower curvature limits, indicating it is a more wrinkled flame surface. And for equivalential 0.6, the curvature is more centered within higher percentage near 0. It means it's more smooth. Sorry, but we see a shift between the experiments and the DNS modeling. We can see for the experiments, the PIV mean experiments, the results is just around the 0 curvature, but for DNS modeling, it shifts to the right. Maybe the DNS modeling is the flame structure is more wrinkled in DNS modeling, but we are not sure right now. Maybe we can do more analysis and investigation on this. So this is the conclusion. So our study just used DNS modeling with line species chemical kinetics. So for the hydrogen air flame, the most important parameter is Lewis number, which means the Lewis number much less than the unity leads to the highly wrinkled flame surface with a cusp-like cells and the diffusional mass and thermal and mass diffusivity also the key contributors. We also do the analysis on the role of species, the heat release rate, and the reactive species distributions are distributed in the high curvature regions, and the high hydrogen mobility is also the key parameter to the cell development. So I'm thanking for the EPSRC for the financial support, and thanks for the CS and the university for the joint scholarship. And we are grateful. We are all grateful for the support from the Computational Science Center for the research communities, and all results, all the simulations are conducted in the Arch2. Well, thank you very much.